Okay, this is our second um, lecture for nuclear chemistry. And today what we're going to talk about is we're going to talk about the rate of radioactive decay. Now, the rate of radioactive decay is the same as our first order kinetics law. And the reason why this happens is the rate of change is the amount of the radioactivity is constant, and it's different for each of those isotopes. So this is how much of that material is going through a decay process. Right, so we talked about the four different ones: the alpha decay, beta emission, right? Electron capture, electron emission, and so we went through positron emission. There we go, and we talked about the different types of decay. Now, the rate of radioactive decay, it's not affected by temperature, and so it's not a chemical reaction, but everything else does follow that first order kinetic rate law, which means that our rate is equal to some K value times N, where N is our number of radioactive nuclei. So if we had that per volume, then that would be like a concentration. It would be just like our other equation. But right now we can kind of think of it as rate being whatever that radioactive decay constant is times the number of nuclei. And so our half-life is going to be ln2 divided by k, just like we had for our half-life of a first-order reaction. We just had a different n. Instead, we had an a. So the shorter the half-life, the more nuclei decay every second. And then they describe that kind of as being hotter. So when they say that there's a hot substance, it's because they're measuring out those radioactive decays. And because decays can release energy, then sometimes we call them hot, because there's a physical temperature that can be associated with certain types of elements as they decay, because they're releasing that energy in the form of gamma rays, perhaps, right, is an example of one. But it doesn't have to always come with a physical temperature change. Sometimes it just means that there's more nuclear decay. And so this is an example of some of those half-lives. We can have a really short half-life, like we see with radon-220, or we can have an extremely long one, like this thorium-232. Just remember that half-life is the amount of time it takes for us to decay half of the initial atoms. So for us to go from 1 million to 500,000, in this case took 1 minute, which is our half-life. And so by minute 2, it's not that we've gone down by half, it's that we've gone down by half and then half of that half. So we go down to 225 or 250,000. And so our amount of decay slowly decreases each half-life because there's not as much initial material. But it stays constant how long it takes us to get to half of whatever material we had from before. And so this is our expression for our integrated first order. We've only changed this, instead of being ln of a t over a naught, we've gone ahead and we've changed it with our k. Now, this is written in your book is slightly different. Instead of using your K, you guys use this lambda. Both of them mean the same thing. It just is, one way is your lambda just stands for that decay constant. And so it's just one way for them to kind of distinguish whether it's a chemical reaction going through this process or whether it's the radioactive decay going through that process. Now, looking at this graph, we want to figure out that, well, radon is the second leading cause of lung cancer in the United States. Determine the half-life of our radon-220. So this picture actually already gives it to you there, so we know it's 1 minute. But if we wanted to, what we would do is we would choose several points. Right? So we could take a 1 point at 1 million. We could take a second point and a third point. And we're looking for when it went to half. So we could draw a line at 500,000, and we could see what time that took. So that took 1 minute to get there. From 500,000, we know that our next one is going to be at 250. So if this was 300, and this must be 250, draw that line. You can see it's at 2 minutes. And so we could do that throughout. We can look for, from 250, we need 125. So this was 100. And so each time we can see that every 1 minute, we lose half of our concentration. And so our half-life should be 1 minute. So keep that in mind as you're going through. You do want to be able to visualize what a half-life is. You should be able to solve for that. But we can also mathematically solve for it as long as we have our K. Now, this is really useful. We use this in what we call radiocarbon dating. And the idea is that once we know the half-life of that carbon, we can look at the concentrations of the material that we have. We can get an idea about what time things have been, or how long it's been decaying for. So radiocarbon dating is an example of this. And so we know that there's 3 isotopes of carbon in nature, and one of them is radioactive, carbon-14. And so carbon-14 has a known half-life, 5,730 years. Now, currently, atmospheric chemistry is producing carbon-14 at nearly the same rate it decays. So that ratio of carbon-14 to carbon-12 has stayed constant through our lives. So while you're still living, your carbon-14 and carbon-12 ratio is constant because we're constantly replenishing its supply of carbon through all of our biological processes. So we might eat plant material. That plant material has carbon-14 incorporated in it. Right? And so we're constantly exchanging with our environment. And so our ratio of carbon-14 to carbon-12 remains constant. Once an organism dies, though, whether that's a plant or an animal, then we no longer get that exchange. At that point, instead of replenishing our carbon-14, we can only turn carbon-14 to carbon-12. So our amount of carbon-12 constantly goes up, and the amount of our carbon-14 will constantly go down. There's no more exchange because our atmospheric chemistry isn't regenerating that carbon-14 for us because we're not bringing it into our system. So our ratio slowly starts to become smaller and smaller as more of that carbon-14 decays into carbon-12. So by measuring that ratio and comparing it to the ratio of a living one, we can tell roughly how long ago the organism was alive. Now the limit is about 50,000 years old. Normally, after that amount of time, our carbon-14 has gotten so low in our background radiation, we can't really tell. It's hard for us to measure the ratio to get an accurate result. So you want to keep that in mind. That's how we do things like carbon dating. Now, there are different types of radioactive dating. Carbon is just one of them. So sometimes when we talk about dating a dinosaur using radioactive or using the different dating process, we can look at other species as well. There's another one called uranium dating, which is normally what we use for minerals. And you can see its half-life is a very different order of half-life, right? 4.51 times 10 to the 9 years. So that's how we can measure the age of, like, let's say the Earth, is by looking at those type of ratios. So if the half-life of carbon-14 is 5,730 years, how long would it take to decay 100 grams of sample to 6.25 grams? So we should be using our ratio here. We have ln of our NT over NA equals. We know that T1 half is ln 2 over K. And so we can change that over. We can first find our K and then use that to find our ratio. So ln 2 divided by 5,000. this becomes 0.12345. There we go. We can now take the ln of 100, or 6.25, divide by 100. And then we can use that to solve our time. And don't forget that there should be a negative sign right here. And so we get our K as being 22,920 years. There we go. Now, nuclear changes can also occur in a different way just besides, outside of only decay. And so these processes can happen between two different ways. One is called fission and the other one is called fusion. Fission is splitting a large nuclei into two smaller ones, right? So this is us breaking something apart. In the same way that a fissure is kind of like a crack in the ground, it's the piece of material becoming two. Nuclear fission is us taking a large nucleus and splitting it into two. Fusion, on the other hand, is when we take small nuclei and we smash them together to make a larger nucleus. Now, both fission and fusion release a lot of energy through that process. Fusion releases more energy per gram than fission. And fusion generally happens with our smaller elements, and fission happens with our larger elements. So a fission reaction is what we're going to talk about first. This is traditionally what we think of when we think about a nuclear reactor. Right? And so a fission reaction is a chain reaction, which occurs when a reactant in the process is also a product of that process. So in fission, the process, what we're going to do is we're going to take our nucleus, we're going to allow that to break up into several pieces. Those several pieces then react to start like a cascade of reactions. So in this case, it released these neutrons inside of that fission process. Those neutrons collided with other uranium particles that started off. Those uraniums then go through their fission process, releasing more neutrons. Those neutrons then once again bombard and collide with more uranium and keeps that process going. So in general, our fission chain reaction kind of uses its energy and its first initial process to keep that process going. Now, in this case, we're looking at that neutrons. That's what's driving that process forward. And so we only need a small amount of neutrons to start that chain, because if each one releases 3 neutrons, then those neutrons can interact with 3 more atoms. Those 3 atoms release 3, and so we can grow from there. Now, a lot of those neutrons that are kind of produced in the fission process are either ejected from the uranium before they hit another U-35, so they might be released out, or they're absorbed by the surrounding U-38. So not all of them go towards driving this process forward, but some of them do. And what you need is you need to hit critical mass. What that means is this is the minimum amount of isotope where we can sustain the chain reaction. Now, as that process continues to grow, right? So as more of these neutrons get produced, then your critical mass can start to overheat, right, or overreact. And this is where we get what we call a nuclear meltdown, right? So you have to put safeguards in there in order to absorb some of those neutrons so you can control how many of those neutrons are hitting other uraniums to drive that process. So the ones that hit that U-38 aren't going to drive that process. They're going to be removed from the process. And that's kind of like how we can slow it down a little bit. Now, this energy for fission, where it comes from is that some of the mass of the nucleus is converted into energy. So if we look at U-35 and we look at its decay process, each of its U-35 that goes through this process actually releases 1.7 times 10 to the 13 joules of energy for every mole of fission. Now that's a huge amount. And what we can do is we can find this by looking at our reactants and our products and comparing their mass defect for that change. So if we look over here on the left-hand side of our nuclear reaction, it's basically our uranium plus the neutron that it gains to kind of drive that process forward. And so it gets a mass, when we add those up, of this. On the other side, we have our barium and our krypton. They have their masses. Plus we have 3 neutrons, and so 3 of them here. And we can add them up and we can see that they're smaller in terms of mass than that uranium. So if we wanted to compare them, we could take that subtraction, that difference. We could take that difference and we can convert it from AMUs into kilograms. Once we have it in kilograms, we can put it into that equation E equals mc squared, and we can turn that into joules because our joule is a kilogram meter squared second squared. And you can see that there's a ton of energy that gets released as it goes through that process. Now this is the joules per 1 atom. And so if we take that, or 1 nuclei really, and we multiply that by 6.022 times 10 to the 23, that's how we can convert this to 1.7 times 10 to the 13 joules per mole. So our fission ones happen with our larger products, and we're getting that energy as we split those nuclei into smaller ones. So fissionable isotopes, they include the uranium-235, plutonium-239, and plutonium-240. Now, very little uranium is actually available to go through this fission process. Most of it is 238, which doesn't go through it. And so in order for us to use fissionable uranium to drive this process forward for, let's say, a nuclear power plant, then we have to enrich it. So we have to try to concentrate this uranium-235. So that way, some of this 235, those neutrons will collide with other uranium-235. If there's not a high enough concentration, then too many of them will get lost, and we won't be able to keep that process going. And so our nuclear power plants use this process here. You can kind of see them inside of that reactor in order to produce electricity. And so in reality, what they do is they use this to produce heat. So as we take that energy that's going through from the fission process, we're using these control rods to absorb the different amounts of our neutrons being released. The more those rods are pulled out, then the more those neutrons will find other uranium-235. When those control rods are placed inside, then they help absorb that neutron, which prevents them from, or helps slow down the process as that those neutrons can't go on to then collide with other uranium-235. As the fission occurs, that fission releases all that energy. That energy is in the form of heat. And so that heat's used to boil water. When that water turns into steam, that steam turns a turbine, and that turbine is what we use to generate electricity. So about 20% of the United States electricity, according to our book, is generated using nuclear power. So the nice part about it is it uses about 50 kilograms of material, and that is enough electricity for 1 million people. There's also no air pollution. On coal burning plants, that same amount of electricity would need to be generated by 2 million kilograms of fuel. It produces that NO2 and and sulfates, which can lead to acid rain. Plus, it adds all that CO2 in the form of greenhouse gases. But the challenge with it is that there are other materials that kind of get used that we have to hold on to. So one is that when water loss happens from the core, then the heat can melt the core, and we can basically have a nuclear meltdown. So this is that when things go wrong, it can really go wrong because our fission process becomes self-sustaining once we have enough U-35. And so once that happens, then if our water is lost, or our, then there's no way for us to stop that process. And the other one is that our waste is highly radioactive. And so right now, we're still trying to figure out what to do with it. Right? Now, sometimes what that looks like is that we're kind of building a permanent nuclear storage facility. And so that's one option. It's a hard situation because you want the half-lives on some of these radioactive materials is thousands of years. And so you want to make sure that your material is going to be stable, be stored for thousands of years. The other one is that if it starts to leach out into groundwater, then it can spread radioactive materials through your groundwater. The other one that they were trying to look at is more about how can we reprocess that uranium, or not uranium, but the radioactive materials. Is there a way for us to convert it into a different isotope that might be more stable, or in a different form that might be more stable? How do we transport that waste safely? And then the other one is like, what do we do with the nuclear power plant itself when we no longer operate them? And so like an example of this is the Yankee Row in Massachusetts. And so there was some concerns about the reactor pressure vessel that was starting to get brittle. And so they wanted to shut this down. And so the Nuclear Regulatory Commission declared that it was going to be decommissioned in 2007. Now, in total, it cost about $508 million to build, right? And this facility ran for decades, right? And produced a significant amount of electricity. And most of that radioactive material, as it was produced, was then kept on site. So after we went through and we produced that electricity, the leftover nuclear waste was stored underground at that site. It has about 533 spent assemblies. Each one is about 800 pounds. The challenge, though, is that they are then placed into these dry casts where we surround them with 21 inches of reinforced concrete, a 3-inch steel liner, and now each cask weighs 100 tons. So there's 16 of these casks down in the nuclear power plant that's been decommissioned. And so right now we're still trying to make our permanent storage facility over in the Yucca Mountains. But until we have that permanent storage facility, all of that material just sits underneath that decommissioned power plant. And so nothing can be done there. And so it is a challenge of nuclear. It's cheaper to make. It lasts for a long time, but it is a challenge with what we do with the material at the end. So the different components are, we have like the fuel rods. The fuel rods are basically that fissionable material. Now, each of these is kind of not quite enough of our, so we have the fuel rods. Then the other ones are our control rods. And so our control rods are made of neutron absorbing material, things like borium or cadmium. And so they're going to absorb these neutrons in order to prevent the reaction from self-sustaining. And then last type of material that we can have is called our moderator. And so moderator is kind of like our neutrons that we're going to, our neutron source. So what we can do is that each of our fuel rods can be kind of subcritical. They might not have enough of a concentration of uranium to run by themselves. But when we put in a little bit of moderator, that moderator injects just enough neutrons that are needed to activate that uranium-235 and engage that process so it can hit critical mass. And so these are all, this is a like broken down example of a nuclear water one. This is called a light water reactor. The nice part about it is, like, with a water reactor is it's being your coolant and your moderator. Pretty much you're using the same material as before. We're just using that water to capture the heat, the neutrons that get released. And so we can use that for our process as well. Now, an interesting fact about this was that when we started to mine different uraniums, what we kind of found out was that there was a certain place in Oklo where the uranium ratios were very off. Instead of being our U-35 at this 0.72, it was at 0.71. Now, because the half-life for uranium is so long, that seemed unusual. And so what they found out is that when they mined ore uranium from this one, it always had that ratio of a low U-35 to U-38 compared to everywhere else. And so the hypothesis is that at some point, there was a natural fission reactor at Oklo that by chance, the uranium was at a higher concentration at that time, because in the past, this ratio was always going to be up, and this one was going to be down because not as much material had decayed. And so we had more uranium-235 there. That process was then interacted with the light water. That water became the moderator as well. And so it helped drive that nuclear fission all by its own. And so naturally, we made a nuclear fission reactor that ran for millions of years, and it converted a significant amount of that uranium-235 to uranium-238. And so just by chance, nature had made its own nuclear reactor, releasing all of that energy. So when we're going to start this one, we want to remember that our binding energy is equal to our neutrons plus our protons of our nucleus. And we know that the mass of the nucleus is that 55.921 AMU. Now, be careful on this. If our nucleus is including our electrons, so if it's just giving us the mass of the atom, then we have to subtract our electrons from it. But if they're giving us just our nucleus, then we're okay, because we're looking for the nuclear binding energy. So we're only concerned with the mass defect of the nucleus, which means that we only care about it without the electrons. So we have to remove those one way or the other. So right now we have our protons, and so we should have 26 protons. We have 30 neutrons. And when we go through that, we should be able to find our mass difference. Now, to help with this, remember that 1 electron volt is pretty much the charge of our electron times the volt difference to bring it to 1 volt potential difference. And so that is 1.60 times 10 to the negative 19 joules per 1 electron volt. And 1 AMU is 1.66 times 10 to the negative 27 kilograms. Once you work your way through that, we're looking for mega electron volts. So think about what that means. And so with our numbers, as we put them in there, we should end up with 492 mega electron volts. So the other type of nuclear reaction that we could be interested in is we had fission. Now we can also have nuclear fusion. Now fusion is a little bit different. Fusion is going to be when we take two lighter nuclei and we combine them to form a heavier, more stable one. This generally ejects neutrons at a high energy. And so nuclear fusion is kind of what the sun uses to provide its energy. Now, the thing about fusion is it requires a high input of energy to initiate the process. And that's because in order for us to fuse those nuclei, we have to overcome their repulsions between the positive forces, right? So that's a lot for us to overcome. But once we do that, then the new force that forms inside, the strong force that's binding our nuclei together, because it's a more stable, heavier nuclei, is even stronger than those forces when they were apart. And so fusion produces 10 times the energy per gram than fission. The other part is that the nuclei that they produce are not radioactive, so there's no radioactive byproducts. Unfortunately, we don't have a working application outside of the hydrogen bond because of this high input of energy. So when we look at it, a fusion reaction can release significant amounts of energy for each one of those nuclei. And so if we had a mole of it, it would be a tremendous amount of energy. We've seen this. This is what's going on inside of the sun. But the challenge that we run into is this input. That so far we haven't been able to initiate a fusion reaction where we don't produce, or that doesn't require so much energy to start that we're able to recover all of that in the end. There are processes where we have been working towards building that. And so one of them is that we can bombard the nuclei with other ones. And so we can do this in what we call a particle accelerator, right? Where we are basically going to keep driving an atom around and around in a circle until we have enough energy there to bombard or collide our particles together. And so while nuclear fusion has happened, we just haven't been able to make it in such a way where we can use it as an energy source yet. But it is the kind of the thoughts about where we could get another new source of clean nuclear energy. And so we can go through, one of the ways that they do this is through this artificial transmutation. And so they can bombard the nucleus with another new atom. So we can bombard them with neutrons. And so we can smash these high energy particles together, and then we can try to produce new nuclei. So this can be either for a fission process or a fusion process. And it's actually one of the very interesting ways that we explore theoretical physics as well as theoretical chemistry, is by trying to get these very high energy particles and looking at the materials that we make. So this is one way that they discovered new elements, is to use a particle accelerator to bombard those particles with different neutrons, protons, positrons, trying to create new nuclei. They come in many different ones. One is like the Large Hadron Collider, right? That's one where you collide these particles at a really high speed with a large energy. We also call them synchrotrons or cyclotrons. And we even have one in Berkeley where they were doing a lot of their chemistry when they were looking for new elements. And so these devices are huge. They can be miles across. The Large Hadron Collider stretches across 3 countries, I believe. It goes into parts of Sweden, as well as the surrounding countries around it. And so they are huge installations that require billions and millions of dollars to build, right? So they're huge, huge instruments. because they need this space in order to send this path of this proton beam and then accelerate it to get to enough energy and enough speed to overcome those repulsions between the nuclei. Now, when we're looking at radiation, the things that we want to know about radiation is there's kind of different levels of radiation, not only in the amounts produced, but also the energy that they have. And so one thing to be aware of is that we're looking for ionizing radiation when we're thinking about things that are harmful to us, right? Ionizing radiation is radiation that has a high enough energy to knock electrons from molecules and break bonds. So this means that that radiation isn't just releasing energy that's going to heat things. It's not going to release energy that makes things vibrate extra large. This is actually where we can make ions. Energy transfer to cells can damage those biological molecules and cause malfunctions of the cells when we get into that ionizing radiation. So acute effects of radiation is something like if we get a high level of radiation over a short period of time, then we can kill a large number of cells because we can ionize a lot of them. And it can cause a weakened immune system and lower ability to absorb nutrients as a result. Chronic ones, so low doses of radiation over a large period of time, it can do things like the increased risk for the development of cancer because you can have your cells mutating. You can have radiation damages to your DNA that won't be properly repaired. Excuse me. And then that can lead to different genetic defects over time. So radiation is something that we do want to be aware of, and so we do want to measure our radiation exposure, and so sometimes they do that in terms of a Curie or a Gray, depending on which different types of are rad. These are all three different ways for us to measure a radioactive exposure. A Curie is just looking at your events. It doesn't care about how what type of radiation it is. And then the other ones are used more when we're looking at body tissue, right? So we're trying to measure your dosages. Now, radiation has a lot of different uses for biological effects. And so generally, what we want to do is we want to keep our exposures low. And so it's a fine balance between using our radioisotopes to give us important information while trying to minimize our exposure to the amount of radiation. And so we're always trying to find that balance in that field of nuclear medicine. So radio tracers are one way that we can use these isotopes inside of your body to help understand what's going on inside of it. What it is it's a tagged isotope of an element. And because certain organs absorb most or all of a particular element, we can kind of track how where these tagged isotopes are moving inside your body. And so we're trying to find something that's low ionizing, so when you're reducing your amount of exposure, but it still has to be something where we can detect it and measure it with a Geiger counter. And we want something with a short half-life so it doesn't stay inside your system for very long. Now, you can see here, we can follow in this example here, we've put in our tracer. We can look inside the body and we can see where that radioisotope is being uptaked inside the body. And so this can give us some information about whether it's behaving like normal or if there's been a problem, right? If some organ is not doing its job and bringing in the isotope, we can tell that. Or if a different organ is taking in an isotope that it shouldn't be, we can also tell that. They're also used for diagnosis, right? And so this could be when we're looking for different materials, we could use things like positrons in order to get imaging scans. We can use our radioisotopes to tag our glucose. And so it all depends on what we're trying to do. But if we're looking at the body, we do want to make sure that we're using the right dosages, and so we want to make sure we understand how much we should prepare. We should also understand how much should be left over at a certain amount of time. We should also know how much material will remain inside the patient's body at different periods along that process. And so one example is fluorine 18. Fluorine 18 has a half-life of 1.83 hours. And so if 2.85 milligrams of fluorine 18 is injected, we want to know what mass of F18 is going to be present after 3.00 hours. So I'll let you go and work through that. Now, we know that 1.83 hours is ln 2 over k. So my k value should be 0.3788. Now my milligrams is going to be 2.85. So ln of my x over 2.85 is equal to negative k, and my t is 3 hours. So I multiply that by 3. Take the e, the negative value of it. And so x over 2.85 is 0.321. And so I have 0.914 milligrams, and that's what I'm looking for. Now, there are some other non-medical uses of radioactive isotopes. We use them in smoke detectors, right? The smoke blocks ionized air, and so it breaks the circuit. And so that's one way we can tell. You can also use it in insect control. One way that they've done that is they looked at sterilizing all of the male mosquitoes, right? And so that way our insects can't reproduce, and so then they don't carry on. You can use them in food preservation. So if you take a sample of food and you expose it to low levels of radiation, you can kill off all the bacteria and viruses on it, and will help it preserve for a significant period of time. We can use it for radioactive tracers inside of chemistry. So if we want to follow where our chemistry is going, then that's one way to do it. When I was in grad school, we used it for carbon-13. And what we did with this isotope was we put in carbon dioxide as carbon-13, and then we measured to see if it was produced in the nanomaterials that we were producing. And so that's one way we could show that our atmospheric carbon was being captured and produced inside of our structures. And so there's different ways that we can use these radioactive isotopes if we want to follow through with them. It's used in a variety of different materials now. They use it in crime scene investigating. They use it in authenticating art objects, right? Measuring thickness and conditions of industrial materials. And so there's more and more uses of radioactive material. And so we just want to make sure that we're practicing with those. Now, for our class, I won't be primarily focused on the usages of the radioactive isotopes, but we do want to have an understanding of the fusion and fission process. We should understand how those produce energy, what's the basis of it. And then we should make sure that we should be able to solve things like what is the mass that's present after so many years if we have the half-life. We should be able to do some radiocarbon dating for them. This problem there, right? So using our decays, we should be able to use that with our half-life to figure out how much time has passed. And we can also do that same thing for our uranium rock. Very good.